So I posted the lab assignment number 2. So as I mentioned, the goal of this second lab is to design data path of single cycle processor. So what are data path elements? So data path elements of the single cycle processors is kind of instruction memory, register file, ALU, and data memory. Also, data path element also include the other components such as multiplexer or some other component. So, but the major data path elements of this single cycle processor designs are the instruction memory and data memory, register file, and ALU. So you are requested to design these 4 elements, but I think some students are not familiar with design with system Verilog. So actually I posted some relative materials for system Verilog design on the Piazza. So if you see the general resources tab, okay. So if you click the resources tab here, then you can find the lecture slides, the videos, homework, and notes. So note. And sometimes you write something on the PDF file, PDF slide. So I also posted a note here. And then solution, the lab assignment here. And then if you see the general resources, then you can find the these 4 files. And then this file is the some lecture slides for HDL design. So actually, this I believe if you took the digital logic design course, then I believe you already learned how to use Verilog, or how to perform the ITL design with Verilog. But if you did not take, then you can see that this slide. Okay, so you can find how to design some very basic logics or some very basic digital system components here. Also, so actually in this course we will use the system Verilog, not Verilog. So actually the system Verilog is the extended version of the Verilog, and then Verilog is a widely used hardware description language in industry. So, but Verilog in Korea, in South Korea, the Verilog is more popular than system Verilog. But I believe the system Verilog is more convenient, and then also system Verilog includes the more enhanced features compared to the Verilog. So in this course, I select the system Verilog for HDL. HDL means hardware description language for RTL design. So, and then there can be some differences between system Verilog and Verilog. So I also posted this document, the system Verilog versus Verilog in RTL design. And then if you read this document, then you can find what are different between system Verilog and Verilog. Also, you can find this link, system Verilog tutorial. So if you are not familiar with the RTL design, then you can follow this tutorial. This is I think this is very good tutorial for system Verilog design. It's too slow. So internet connection is too slow, like this. Also, so actually I taught the digital logic design course And then also I posted a slide I made in here. So this is the slide for value design and value test bench design. So actually, in the second lab assignment, for the second lab assignment, you need to design the test bench also. So test bench is used for verifying your design. So I also posted this lecture slide for making test bench. So if you have any questions or if you have any issues while you are doing the second lab assignment, please post questions on the Piazza like this. So you can find some Q&A here. So there are many questions on the Piazza. Okay. So you can make use of this very good class management tool. Okay, so let's go back to the lecture slide. Okay, so in the previous class, we learned how to design single cycle processor. So in the chapter 4, we first start from how to define the operation of executing instructions in computer processor. So first we define operations of each step. So actually I distinguish the instruction execution as 5 steps: instruction fetch, instruction decoding, execution, memory accesses, and write back. The most of instructions follow these 5 steps, and then we learn how to design data paths. So what are data path elements? Data path elements are, or data path element is a component that handle data used in the computer hardware or some memory component. So actually in the single cycle processor design, what are memory components? Instruction memory, data memory, and register file, because the data handled by some instructions are stored in these memories. So also I mentioned that instructions are also data. So the instructions are stored in the instruction memory. And then the data handled by load and store instructions are stored in the data memory. Also operands used by every instruction is stored in the register file. So those are the memory components. So we define the operation of the data path element, and then we define, and then we learned that these data path elements need control signal, because based on the different instructions, data path needs the different operations, like memory read or memory write by load and store instructions. So it means we need the control unit and control signals. So control signals are generated from these control units, and then these control signals are generated based on the instructions. Okay. And then finally, we connected each data path element, and also we connect the control signals to the data path. Then we can complete the single cycle processor. And that's it. I think I said it's done for designing single cycle processor. So In the previous class, we learned until this slide, so data path with control. So based on these steps, the definition of the each operation of the each instruction, and then data path design, and then control unit design, and then connecting these components to each other, then we can complete the single cycle processor. So this is the diagram or hardware description diagram of the single cycle processor design. Okay, so as you can see, this is the abstracted diagram. What does that mean? If you see this figure, then you can find many rectangles, like it's a PC, or it's a memory, it's a registers, immediate generator, some components like adder, multiplexer. So actually, we do not the detailed logic inside of these elements. So it will be very complex. So for example, for the instruction memory, we need to implement this memory with the SRAM. SRAM means the static RAM. So actually the SRAM is composed of many bit cells, and then bit cells are composed of 6 transistors. But we did not learn about the this detailed implementation of SRAM. We just define the memory. So details are hidden. So, but the required operations, such as the address port, and then the data read and the data write. So these operations are defined for these memory devices or memory components. Okay, so then that means we use the concept of abstraction. So this is the single cycle processor design, but as you can see, I only shows some boxes or some diagrams and then connections. And then if you see that these connections or components, then you can understand how this hardware works for the different type of instructions, right? Okay, so I mean, this is the abstraction level we learn and then we handle in this course. So when we mentioned some computer architecture level or microarchitecture level of the computer processor design, then you can understand this level of abstraction. Okay. And then also the following slides define the different operations by different type of instructions, and I briefly explain. Okay, here's the So for the R-type instruction, so if I mention the R-type instruction, then you can find that the example of the R-type instruction is the add. So I frequently use this one, x1, x2, x3. So let's see how this instruction is. Oh, why it doesn't work? Okay. How? Okay. Add x1, x2, x3. So let's see how this instruction is executed and processed in this single cycle processor. And I believe you already, most of you already know how this instruction is executed, because I repeatedly explained the data path, also some control part, so this single cycle processor design. So you can think that this is the kind of review, okay, for how instruction is executed. So I mentioned that the instructions is stored in the instruction memory. And then this instruction is accessed by PC. So PC is an address for instruction. So this PC for this add instruction is defined. So defined that means that this program counter register have the corresponding PC address for this add instruction. So it becomes the current PC. So the instruction memory is accessed by this current PC address. Then the instruction memory generate output the instruction, the corresponding instruction. And we already know the size of this instruction of RISC-V. The size of the instruction is 32 bit. So instruction is out from the instruction memory. So as you can see, these instructions goes to the control unit and then the part of the instruction. So if you see the instruction format of the R-type instruction, then you can find that the part of the instruction bits are assigned to the source register number 1, and then source register number 2, and then destination register number. So this is the RS1, so RS2, and then this is RD. So among instruction bits, some bit field assigned to the corresponding register numbers are given to the registers. And then, as you know, the R-type instructions R-type instruction includes 2 source registers and 1 destination register. So these register numbers are given to the register file. And then if the source register is given, the corresponding data are out from register file. And then this is the R-type instruction. So we don't need this R-type instruction does not include immediate value. Why? Then the control unit generate the control signals based on the type of instruction. And then if we see the OP code field of instruction, they can know the type of the instruction. Oh, this is the R-type instruction. Then the ALU OP is set as the, I think it's the 1X. X means the don't care. And then what is this number, this value? The ALU source is connected to here. So what is this value? 뭐죠? What is the value of ALU source? 0, right? It's a 0 because I said, oh, this is the R-type instruction. R-type instruction requires 2 source registers. So that means these R-type instructions requires 2 data from register file. So that means that this read data 1 is read data 1 comes out from this register file, and then this is directly connected to the 1 input of ALU, the first input. And then how about the second input, second operand of the ALU? So if you see that this second input port of the ALU, you can find that this port is connected by multiplexer. So that means the multiplexer select from 2 inputs, and then the output is selected from the 2 inputs. And then as you can see, one of the input is the output port of the register file, and then another input is connected to the immediate generator. But this R-type instruction needs operands from two operands from O register file, right? So this port should be connected. So this port, and then if you see that this figure, then that means that the selection signal should be 0. So how that? So this port is connected to the ALU, the second input of the ALU. And then this R-type instruction, the result of the ALU is written back to the register file. So this data should be connected to the this write data port of the register file. So that means this selection signal should be also 0. So this is the 0. So based on the OP code, we can decide the values of control signals. Okay. And then this is the R-type instruction. And then if the R-type instruction is executed, then the next instruction, the program count of the next instruction is arrays PC plus 4. So current PC plus 4. So I said this is the current PC. And then this add. So this is the current PC plus 4. And then this current PC plus 4 becomes the next PC of the next instruction, right? And then I said this program counter is synchronized by clock. So that means the next PC value is updated to the program counter output at the rising edge of the clock. So that's how the R-type instruction is executed in the single cycle processor. And then it's the same to the load instruction. And then like a load x1, like x2. So load instruction include the immediate value for offset of the data, offset of the address. So actually the instruction read is the same to the R-type instruction, but as you can see, this load instruction, in order to generate the address of this load instruction, the ALU is required, but ALU receives one of operand from the immediate value. So the selection signal for this mux should be 1, because this port is connected to the output of this multiplexer, and then this port is connected to the output of immediate generator. Okay. Oh, you can find that. Oh, also the same instruction is connected to this register. Yeah, that's right. So actually these bits of instructions are also connected to the register file. So this register file generate some output data for this read register number 2. But this data is ignored, so blocked by this multiplexer, and then this data is not used. So that means the garbage data, so garbage value can be given to this register file, but the data output is not used, so we can ignore this data. So it's negligible. So that means any data can be given to this port, right? And then address is generated from this ALU, and then this That means the output of the ALU is directly connected to the address port of the data memory, and then the data memory generate the corresponding output based on this address. Okay, and then if for the load instruction, the return back data comes from the data memory, right? So the selection signal for this mux should be 1. And if you see this is the 1. So when the load instruction is executed, then we can find that the program counter is used, instruction memory is used, register file is used, immediate generator is used, and then ALU is used, and data memory is also used. And then how about the PC? And the PC is the same. The next PC is the current PC plus 4. So this part is not used. And then how about the PQ instruction, like PQ, X1, X2, target. So target is the actually immediate data, immediate value. And it's the same. This instruction is read from the instruction memory. And then as you can see, this instruction requires 2 operands from register file. So this port is activated, this port is activated, but BQ does not require any write register. So that means that the BQ does not require any destination register number. Oh, but also we can find that the part of the instruction bits are connected to the write register. So and then this is just a wire, so it's a physical wire. So that means the electric signals are given to this register file. So actually the garbage data, as I mentioned, the garbage data is given to the registers. That means some bits from instructions 11 down to 7. But we know that in the BQ, the data is not written back to the register file. And then this is controlled by read-write control signal, right? So for the BQ, the read-write should be what? This signal should be 0, right? Because as I mentioned, the data is not written back to the register file. So we need to disable the data write to the register file, sorry. And then for the BQ instruction, we need to compare these 2 operands. Then we'll use the ALU. So ALU receives 1 data from the register file here, and then another data from the register file also here. So this ALU source should be 뭐가 되죠? 0, right? Right. And then the ALU performs the x1 minus x2, so the subtract operation, and then 0 is detected. So if the 0 is detected, that means if the values are the same, 2 values are the same, then this 0 becomes the 1. So, and then based on the OP code, the branch will be 1. Branch is 1 for the branch instruction, because it's a BQ. So it is 1, this is 1. The output of this AND gate is 1. So if this output of the AND gate is 1, then this port is selected. What is this port? Oh, this port this is the adder, and then one of the input of this adder is the current PC, and then another input of this adder is the immediate value by 1 bit. So this becomes the target of the branch instruction, and then based on the condition of the branch instruction, the next PC is selected from PC plus 4 or the target of the branch instruction. Okay, so when the branch instruction is executed, this instruction use program counter, instruction memory, register file, immediate generator, and then also this part. And this AND gate, also ALU is used, multiplexer, this multiplexer is used. So I showed that this single cycle processor support the 3 different type of instructions, like R-type instructions and memory instructions such as load and store instructions and branch instructions. Okay, and it's done. We found that this is the this single cycle processor is working for the selected instructions, right? And then, but it's done. The processor is designed, and then processor is working for the selected instructions, and then that's it. So that means this processor, the design of this processor is done, and then this processor will support the selected RISC-V instructions. But there are performance issues. So what is the performance issue of this processor? Actually, this processor will support the some defined selected instructions like load, store, and then add, or sub, and, or, and BQ. And that's it. So what is the performance issues? What are the performance issues? So this is the system design. And then this is the single cycle processor. So that means in a single cycle processor, all instructions should complete each operation within 1 clock period. Okay. So in the first time of this chapter 4, I defined the 5 steps of executing instructions like instruction fetch, instruction decoding, execution, and memory access, write back. Oops. So these all operations should be completed within 1 clock period, like this period. Okay. Also, in the system design, the critical path, the critical path is the longest delay of the processing. So this critical path decides the clock period. So what is the critical path of executing instructions? That is the load instruction. So why? Because when I mentioned about the load instruction, this load instruction requires to access instruction memory, register file, also ALU for address generation, and then accessing data memory, and then return back to the register file. And then that means when this load instruction accesses these data path element, then it will take some delays. So when I first thought about the digital system design conventions, so digital system this looks like this black box. And then this logic receives some input and then generate the output based on the input signals. But this output is generated after some delay. So it will take time. And then the load instruction touches every data path element. So the delays of this load instruction will be the longest. Okay, do you understand? So the delay of these data path elements, that means the delay of the sum of the delays of each data path element will be the critical path, the delay of the load instruction. And then this delay of the load instruction decides the clock period. So why clock period is critical for the performance? Because the execution time is the instruction count multiplied by CPI multiplied by clock period. So if the clock period, this clock period is high, then the execution time will be increased. So if the execution time is increased, the performance is degraded, because the performance is inversely proportional to the execution time. So then for the hardware, so in this equation, we cannot change the instruction count because this is determined by software and ISA and compilers. The hardware cannot decide the instruction count, right? So determined by hardware. And how about the CPI? CPI is for the single cycle processor is what is the CPI of the single cycle processor? 뭐죠? It's one, right? Because I said that every instruction will consume one clock. That's true. This is a single cycle processor. Okay. So it's one, it's a fixed value. Then the execution time is decided by clock period. Well, when you see the this, so when you see the clock period of the single cycle processor, then we can find that the capacity is too long. So that means the delay of this load instruction is too long. And then that means the delay becomes the sum of the delay of each data path element. Then if we reduce, and then if we can reduce this clock period of this processor, then we can improve the performance, right? But in the single cycle processor, we cannot reduce the clock period of this single cycle processor, right? Because the critical path of this single cycle processor is already determined by the summation of each data path element. So in order to improve the performance, that means in order to reduce the clock period of this system, we need to apply pipelining. Okay, so pipelining is the next topic of this course, and then our midterm exam will include until here, okay? But we have time, so we need to go to the next step. 챕터 4는 작년 과제 중에서 좀 해당되는 문제를 좀 선별해서 올려볼게요. 예. 예, 과제가 안 나오긴 했죠. 근데 어차피 이제 연습 문제 비슷한 그런 과제가 나올 거고요. 그러니까는 참고를 하면 됩니다. Okay, so and then we have time for this today's class. Then so we need to study pipelining. So this pipelining is also the highlight of the discourse. So actually, so it's the one of the critical goal of the discourse is to understand pipelining. And then this is a very important topic for the digital system design or processor design, because with the pipeline manner, then we can dynamically increase the performance of our digital system design or processors. And then actually, this pipelining concept is widely applied to our real life or some industry. So it's very important. So let's see the pipeline. So this slide shows the analogy of pipelining. So this analogy is very famous analogy because I said this textbook for the textbook for this course is very popular in the computer architecture field. So everyone who study with this textbook knows this analogy for pipelining. So like this is the pipelined laundry. laundry가 세탁이죠, 세탁. So some laundry processing. So for this laundry processing, so the first step for the laundry is to use the washing machine. So this is the washing machine, 세탁기죠. And then when the washing machine, after using washing machine is done, then you can use the dryer, the 건조기죠, dryer. And then with the after using dryer is done, then you can fold the clothing, and then you can store the folded clothing to the closet. So these are the required steps for laundry, right? And then there are 4 different steps for this laundry, like washing machine, dryer, folding, and storing. And then for the one clothes, like one shirt, we can apply these 4 steps for one shirt, one clothing. So, and then done. And then, but we already know that we have many clothings. That means we have many shirts shirts for laundry. Then we can start the laundry for another shirt. Then washing machine, dryer, folding, storing, and done. 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 Another shirt. Done. So how long will it take? So let us assume that it will take 30 minutes for each step. Then if we start the laundry at 6 p.m., then it will end at 2 a.m. for the 4 different shirts. So what is the inefficiency in this process? what is the inefficiency in this process? So for one shirt, with all 4 steps are applied, and then the another shirt, the all 4 steps are applied. Okay, so actually for this laundry process, we do not take any breaks, right? 우리 안 쉬었어요. 사람은 안 쉬. So every steps are applied to the every shirt. 야, 예. 그래서 중요한 거는 지금 이채은 학생이 말한 것처럼 기계가 that's right. So for this, let's focus on this time slot. We just use the washing machine only. So for this time slot, other steps or other machines are not used. So we do not use the dryer, and we do not we do not fold clothes, and then we do not store clothing to the closet. How about this time slot? Only dryer is working. Washing machine is not used, then folding is not used, then closet is not used. It's the inefficiency. So we can organize the working process like this. It's the pipelining manner. So when this clothing use the washing machine, and then after 30 minutes, then we can use the dryer. But the washing machine is idle, so washing machine is empty. Then we can use this idle washing machine for the another shirt, so another clothing. So for this time slot from 6 p.m. 30 to the 7 p.m., so we can use both washing machine and dryer. But it's possible, right? Because it's a different machines, and then different machines can work concurrently, right? So this shirt A is using dryer, and then shirt B using washing machine concurrently. And then it's the same to the another shirt C and shirt D. So this is the pipelining manner. And then for this time slot, every step is applied. So there is no there are no idle machines or idle processes. Okay, so this is the analogy of the pipelining. So with the pipeline manner, then we can reduce the processing time dramatically, because so when we apply the pipelines, then we can complete the every process until 9:30. So compared to the 2 a.m., we can go to bed earlier. So this is the benefit of the pipelining. And then actually, this pipeline manner is applied to every part of the real life. For example, so you know the conveyor belt of the factory. So like a car factory, the car factory use the conveyor belt, and then each step of the conveyor belt is divided like this, and then this conveyor belt flows from the left side to the right side. So for each step, this is the worker, so another worker, one worker, worker here. So if if this worker performs the A step, and then the next time slot, this A is delivered to the another worker, and then this worker performs the same operation for the different material for car. So this conveyor belt system is very similar to the pipelining. And then why pipelining is used? In order to increase the efficiency. So when you compare the performance, so performance is just to compare the execution time of the this processing and then this processing, and speed up is the 2.3. So that means the performance is improved by 2.3 times compared to this original manner. So this analogy shows that why pipelining is good for higher performance. Okay. And then if there are infinite amount of this workload, so that means the infinite number of shards, then the speed up will be about 4. And then this speed up is very similar to the number of stages, right? It is because for this non-pipelining system, this system will complete the one shirt, one laundry for the one shirt will be completed in 2 hours. But for this pipelining manner, this process will complete the laundry for one shirt in every 30 minutes. So that's why the speed up for the infinite amount of workload, the speed up will be 4. So that is the benefit of the pipeline. So, and then as some students said, with the pipelining, we can make every steps or every machines work concurrently, right? And this is very important for industry and also in the systems. Okay. Okay. The start of the chapter 4, I defined the 4 different steps for executing instructions, like instruction fetch, instruction decoding, execution, memory, and write back. And then that means we can divide the steps for executing instructions like these 5 steps, and then the pipelining can be applied for these 5 steps. So what does that mean? So in this analogy, it's a laundry analogy, then the process for laundry is composed of 4 steps. And then these 4 steps, pipelinings are applied for these 4 steps. So that means that each time slot is applied to every step, like one step. Then, but I defined the executing instruction requires 5 steps. That means the pipelining can be applied to the 5 steps of these executing instructions. So that means we can organize the pipelining of this processor as 5 stages. 1 stage for instruction fetch, 1 stage for instruction decoding, and execution, memory, write back. Okay. So then that's the performance of the pipelining. So let us assume that the delay of the instruction fetch is 200 picosecond, and then register read 100 picosecond, ALU 200, memory access 200, register write is 100 picosecond. And then for the single cycle processor, I mentioned that the longest delay, that means the critical delay of the critical path decides the clock period of the single cycle processor. This is the load instruction, and then as I mentioned, load instruction need to touch the every data path element. So we need to add all delays here, and then the total delay of the load instruction is 800 picosecond. How about this SD? SD does not need register write, the write back stage. So it's the 700, R-type instruction 600, BQ 500 picosecond. So this table also shows that the delay of the load instruction is the longest, then the clock period of this single cycle CPU is, what is the clock period of this single cycle processor? 8 picosecond, right? It's the 8 picosecond. Then we want to increase the performance of this processor with the pipelining. So then, as you can see, these steps for executing instruction is composed of 5 steps, and then that means that we can apply the 5 stages for the pipelining, like instruction fetch, instruction decoding, execution ALU operation, then memory, this is the write back. So that means for the instruction fetch, it will take 200 picosecond, and then for the instruction decoding, it will take 100 picosecond, execution 200, memory 200, and then write back will take 100 picosecond. So we divide each step of executing instructions as 5 steps. So that means for 1 clock, so also the first question, so what is the longest delay of among these 5 steps? What is the longest delay? (200 picosecond), right? And then in the pipeline architecture, or pipeline the processor design, the clock will be assigned to each step. So that means, so in the pipeline the design, for the instruction fetch, it will take 1 clock. Register read will take also 1 clock. ALU, the execution stage will take 1 clock. The memory will take 1 clock, and write back also will take 1 clock. So that means in a single cycle processor design, the 1 clock is assigned to one clock is assigned to executing 1 instruction. So that means the 5 stages of executing instructions or instruction. So these 5 steps are the 1 clock period is assigned to performing these all 5 stages. But in the pipeline architecture, this one clock period is assigned to each step. Okay. Then what is the second question is the second question is the what is the clock period of this pipeline processor design? Clock period. 나오죠? The one answer is the 1000. Another answer is the 200 picosecond. The answer is, the correct answer is 200 picosecond. Why? Because I mentioned that this one clock period is assigned to each step. So that means for this delay of the instruction fetch, the 200 picosecond, this 200 picosecond should be less than the clock period, one clock period. Okay, so that is the delay of the instruction fetch. The delay of the instruction fetch should be less than the clock period. And then how about the ID? Delay of the ID should be less than clock period. Then that's same to the EX. Ma'am. Right back is also same. This is because I mentioned that one clock cycle is assigned to each step. Then what is the longest? That means longest delay of this step, longest delay of a single step. That is 200 picosecond. Right. This is the longest delay. Longest delay. Longest delay. So in this 5-stage pipeline architecture or 5-stage pipeline CPU design, the clock period becomes 200 picosecond. Okay. And then it's the same to this analogy. So for this analogy, the clock period of this design is 2 hours because it's the longest delay. But in this design, in the pipeline design, the clock period of this pipeline design is the 30 minutes. Because in the pipeline design, each step will complete within 30 minutes. And then that means the system can receive the new closing. That means the new instruction in every 30 minutes. But how about this design? This is the single cycle processor. It's similar to the single cycle processor design. This design can receive new instruction. That means the new closing in every 2 hours. So that means for this design, the clock period becomes the 2 hours. This design, the clock period becomes 30 minutes. Because this delay decides the clock period. And that's the same to this here. The longest delay of each step can decide the clock period of the pipeline architecture. That is the 200 picosecond. So compared to the 800 picosecond, this clock period is 4 times less than the single cycle CPU. So that means we can increase the performance as much as the reduced clock cycle period, right? Because E is IC multiplied by CPI multiplied by T. So this is the 200 picosecond. Oh, this is the 800 picosecond. But someone may ask that, oh, in the analogy, the performance is improved by 4 times because the every step of the laundry is can be divided at the same with the same period. But this is the 5-stage pipelining, but the performance improvement is not 5 times. So we can just compare like this: E equal IC CPI T. Then let us assume that this is the same. Then we can just compare the clock period. So for this design, the single cycle design is the clock period is 800 picosecond, and then the pipeline design, the clock period is 200 picosecond. And then if we just compare the performance, then it's the performance is that this design is 4 times faster than this design by this equation. Well, it's not 5, even though this is the 5-stage pipeline architecture. Why? This and this is this time, and this time is wasted. So that means the ID stage and write back stage only require 100 picosecond of delay, but every part of the system design need to use the same clock signal. So that means 200 picosecond of period, clock period should be applied to this ID and write back stages, right? So that means even though this stage can be completed within 100 picosecond, but we need to give 200 picosecond of time slot for this ID and write back stages. So 100 picosecond and 100 picosecond is wasted for these 2 stages. So that's why the performance is improved by 4 times, not 5 times. Do you understand? So just the speed up of the pipeline design, if all stages are balanced, like the analogy of laundry, so that means that each step takes the same time. Then the speed up of the pipelining is similar to the number of stages. So like based on this equation. So for example, if we apply the 5-stage pipeline architecture, and then each stage, if each stage can consume 160 picosecond, right? Then the speed up will be 5, because each step is well balanced. But it's not true. Normally it is not true. So if not balanced, the speed up is less. For example, in the previous example, the speed up is 4 because 8 picosecond versus 200 picosecond. It's a clock period. And then speed up is for each instruction. each instruction. Like let's see the load instruction. The latency, how about the latency of the load instruction? It's a non-pipelined version and then pipelined version. What is the latency of this load instruction? The latency means that it's the time gap between start of execution and the end of the execution. For the non-pipelined version, that is the single cycle processor, the latency of the load instruction is 800 picosecond. How about the pipelined version? It's 1000. Because for the pipelined version, it's 1000 because we need to calculate until the end of this clock period, that means the rising edge of the next clock. So that's 1000 picosecond. So if we just compare the latency of one single instruction, the latency is even increased. Then what is improved? The performance, the improved performance factor is the throughput. It's the throughput, the amount of instructions within the same time. So that means in the same time, the pipeline, the architecture can execute more instructions. So you need to understand this, okay? The latency does not decrease, latency can be increased in the pipeline architecture, but the throughput will increase, okay? Okay, so I think I need to mention the hazard next time. The hazard is also the important topic of this pipeline architecture. Okay. Okay. I think we can stop here. So do you have any questions? So pipelining is very important, and then actually the analogy is very simple. I believe that everyone can understand that this analogy of pipelining very easily. And then if we compare just the required steps for the pipelining and then the the baseline ideas of the pipelining, then I believe everyone can understand why pipelining is better than the single cycle processor design. Okay. Do you have any questions? 오늘 수업 내용은 파이프라이닝은 포함되지 않고요. 그 싱글 사이클 프로세서 디자인까지 포함됩니다. Okay, thank you for listening, and then please prepare well for the midterm exam, and then let's see the midterm exam. Okay.